Hi, everyone. Can you all hear me? Okay. All right. So I finished my PhD here at UT about 4 years ago, a long time ago. And now I teach physics at Southwestern University up in Georgetown. So, but I'm really happy to be here today and talk about galaxies, which is what I did my thesis about. And so I wanted to talk to you tonight about how we as humankind kind of discovered the galaxies and essentially the birth of extragalactic astronomy. And extragalactic astronomy just means a branch of astronomy where astronomers study galaxies outside of the Milky Way. So about 100 years ago, astronomers didn't even know that other galaxies existed. We saw the Milky Way in the sky, but we didn't really know what it was. And nowadays, astronomers can look at this image of the Whirlpool Galaxy here, which is about 30 million light years away. And they can tell you with pretty good certainty that this galaxy, just like all galaxies, is made up of stars, gas and dust, and dark matter. We know they can tell you how the gas likely moves in this galaxy, how it rotates. Looking at the structure of the galaxy, they can tell you its evolutionary history, what types of things did and did not happen to it over the course of the last 8 to 10 billion years. And they can probably even tell you the types of stars in the galaxy and the composition of the gas and dust inside of it. So how did we learn so much about galaxies? Back to a time before we knew anything, before we knew anything about galaxies or the Milky Way. And, oh, I forgot to turn on my recorder. Here we go. There we go. Okay. So let's go back to a time when you would go outside on any dark night and the sky would look like this. So imagine that. You go outside and almost every night you see this. And this is a picture of the Milky Way. This was taken about 7 hours west of here in West Texas at McDonald Observatory, because that's how far you have to go to get a sky this dark. And so people for thousands of years would look up and wonder about the nature of the Milky Way. What is this band across the sky? And different cultures had myths and legends about what this was. So the ancient Greeks, for example, thought it was a spray of milk, hence the Milky Way. That the Milky Way was actually composed of individual stars, which is pretty incredible when you think about it. And some Persian astronomers during the Middle Ages also speculated the same thing. But they had no way to test their conjectures, right? They didn't have the technology to test these hypotheses. Until the 1600s, when Galileo pointed his spyglass-inspired telescope at the sky. And he was the first one that was actually able to resolve the individual stars, to see the individual stars in the Milky Way band across the sky. And so he was the first to prove that the Milky Way was indeed made up of individual stars. About 150 years later, the philosopher Immanuel Kant also speculated that the Milky Way was a huge rotating body of stars. And he also, in fact, proposed that it must be in the shape of a disk because of its geometry making a band across the sky. And incredibly, he also speculated that the Milky Way was just one of many galaxies. So for the next century, 150 years, people were studying the Milky Way. Different astronomers tried to actually determine its nature and size by counting stars in different directions and trying to make a map of it and figure out how big it was. And also people, observers, astronomers that would take pictures of the sky started cataloging these objects, which they called spiral nebulae. So this is a really cool picture of Andromeda, which is the nearest large galaxy to the Milky Way. This is a photograph from 1899 of the Andromeda Galaxy. And this is object Messier 77. And so some thought that they were objects in our own galaxy in the Milky Way, and then others thought that they were external galaxies, which at the time was kind of dramatic thing to think, because most people believe that the Milky Way was the whole universe, in fact. And so that led us in the 1920s to the great debate in astronomy, where they debated just this question: is the Milky Way galaxy, is it the whole universe, or is it just one of many galaxies? And so they were on the brink of a great discovery. And in 1924, Edwin Hubble settled this question once and for all, proving that the Milky Way was just one of many galaxies and that the spiral nebulae are actually external galaxies. How did he do this? Well, a few years before that, an astronomer named Henrietta Leavitt discovered that these special stars called Cepheid variable stars had a really interesting property. So their light pulsates, so if you observe them over time, they dim and get bright in a regular fashion. And so she figured out that how fast they dim and bright, how fast their light pulsates, is related to their true brightness. And in astronomy, if you know the true brightness of an object, then you put it really far away and you observe it and it appears fainter, right? Because it's really far away. So if you know how bright it appears to you from Earth and you know how bright it actually is, you can figure out its distance. And so for these stars, it was easy to figure out their true distance just by observing and measuring how fast their light dims and brightens. And so Hubble used the Hooker telescope at Mount Wilson Observatory, and he observed some of these stars in the Andromeda Galaxy, which was one of the spiral nebulae at the time. And he determined the distance for the Andromeda Galaxy, which was so far away that it could not possibly be inside of the Milky Way galaxy. And so he proved that Andromeda was an external galaxy. So where did we go from there? So in the 1920s, 30s, all of a sudden we had this whole new class of objects that astronomers could study. And so that was basically the birth of extragalactic astronomy. And so here are some really pretty Hubble images, because now we have Hubble so we can take awesome pictures of some nearby galaxies. And when I say nearby, I mean that in astronomical terms. So a lot of these galaxies are 50 to 100 or something million light years away, right? But that's to us the local universe. And so as you can see, there's not only just galaxies outside of the Milky Way, but there's all different kinds of galaxies. So a lot of these galaxies look really all the different types, right? And so astronomers decided they would try to come up with a classification system to classify these galaxies based on their physical properties. And they wanted their classification to be such that they could glean something about the true nature, the physical nature and the relationships of these galaxies, and maybe their evolutionary history based on how they group them together. So in the local universe nearby, we generally see three different types of galaxies. So we see elliptical galaxies over here on the right, left. We see spiral or disk galaxies, and then dwarf galaxies. So let's talk in detail about each different type. Okay, so elliptical galaxies first. So elliptical galaxies essentially are giant balls of stars. Except they're not really balls, because a lot of them are kind of elongated. They have what we call a triaxial shape. And so some look like a football. And essentially, they have very little to no gas or dust. And so they're not actively forming a lot of stars. Elliptical galaxies are some of the largest galaxies in the universe. And we usually find a very huge, giant elliptical galaxy at the center of galaxy clusters. So then we have spiral galaxies. So spiral galaxies are a little bit more complicated because they're flat. If we're looking at them from the top, which we call a face-on view, we see their flat part. And then if we're looking at them from the side, you see their edge. So that's a view right here, the side, the edge-on view. And so here's a few examples of disk spiral galaxies. I'm just going to use those terms interchangeably. And you can see there's a lot of variety, right? So let's look in a little bit more detail So, well, the first thing you can notice is that they're very patchy, so that's a lot of gas that they have. These dark things that we also see in the image of the Milky Way, these dark things are dust bands. And then you can see that they have, in the center, a lot of them have kind of a yellow little ball of stars, and I'll talk about that in a little bit. Okay, so let's start with the anatomy of a spiral galaxy. So here we have the face view, and here we have the edge-on view. And so you see these patches here, right? So these are clouds of gas. And in the spiral arms, which is like a traffic jam, and so they kind of get compressed and pushed together. And when the gas clumps together, when it reaches a certain critical density, it'll start collapsing under its own gravity and forming stars. So in the arms, we see these star formation clouds, like this one that's shown here, which is not in this galaxy, it's in our galaxy, but in order to show a picture with a lot of detail, obviously. Use your imagination. Okay, so that's a star formation cloud. So these disk galaxies are forming a lot of stars. They have ongoing star formation. And from the debris of star formation, from the dust debris in these clouds, planets form around the stars. Okay, so let's continue with our anatomy lesson here. Okay, so this main part of the spiral or disk galaxy is called the disk, right? So you see it here, it looks very circular because we're looking at the galaxy face on. And then here it looks really thin because we're looking at it from the side, edge on. So you can tell that the galaxy disks are actually quite thin. In the central regions, we have the bulge, and we call it the bulge because when you look at it from the side, it kind of bulges out. And some spiral galaxies have huge bulges, so they take up they go up to here, most of the way out of the disk. And then some spiral galaxies have really small ones. So bulge we know is made up of mostly older stars, and the disk here is made up of mostly newer stars. Blue stars. In the middle of the galaxy, and the dark matter halo is way, way bigger than the galaxy itself, the visible part of the galaxy. And so that circle is not to scale, but just to show that it's ginormous. Percent of spiral galaxies have is, you see how this galaxy is not circular like this one, it has this elongated thing in the middle. So that's what we call bursts here around the bulge, and it looks really cool. They form a lot of stars. Okay, and then finally we have dwarf galaxies. I'm not going to talk much about these. There's a lot of them. They're really faint and small. There's all kinds of different types that are lumped together in the term dwarf. So some, like this one, this is the Fornax dwarf, they don't have much gas. You can see it just kind of looks like a faint wisp of companions to the Milky Way. And you can tell that they seem like they have a little bit more gas and kind of like amorphous structure. You can't tell if it's a disk or what it's doing. So that's why they're called irregulars. So, okay, so now you might say, well, okay, so there's all these different types of galaxies that we observe, but why? So why, how did they get here? And did they always look like this? And how did they form, right? So luckily for astronomers, time travel of a sort is possible. So we know that light has a finite speed, right? And so when we look at things that are really far away, like for example, this galaxy is NGC 1300 and it's about 60 million light years away. And so you can kind of already tell what that means. If we take pictures of galaxies at progressively greater distances, but we can make a picture album of sorts of all different types of galaxies at different ages in cosmic time, and therefore at different stages of galactic evolution, and piece together a story of galactic evolution. And so that's exactly what we do. So the farther back in time a galaxy is, the farther back in time we are looking when we observe it. So everybody probably knows this image. This is the Hubble Ultra Deep Field. It was taken in 2004, and the deepest image of the universe ever taken. So what that means is that Hubble stared at it for a really, really, really long time. I think it was like 11 days. So they could see the farthest away objects, the faintest objects that Hubble could technically observe. And so, So, and this patch of sky that it looked at was so small, it was like 1/13 millionth of the whole sky. Okay, so here's kind of like a slice in time through this image. And so here in the front slice, we see galaxies that look just like the ones that I showed you. So they're mature galaxies that are kind of present day galaxies. And then as you go farther back, you're seeing farther away objects. And then the faintest things are very distant galaxies that we see as they were 10 billion years ago or so. So let's zoom into some of these guys. Not quite yet. Okay, so here's some boxes of some of the farthest away things, and you can see them kind of zoomed in on the right, and you can see that they don't look like present-day galaxies going on with them. And that's basically exactly what it is you're seeing the building blocks, the small building blocks of present-day galaxies that are merging together into a few minutes. And so let's watch this computer simulation. What you're seeing here, the green filamentary things you're seeing are gas. So this is happening within a dark matter halo. And in the center of the halo, that's where everything wants to fall to. It's the lowest potential well. So the gas coalesces, and as it gets dense enough, it begins to form stars. And here you'll see, I think, things that turn yellow are old stars. And then things that are still blue are newly formed stars, and the green stuff is gas. And so you can see there's a lot of merging going on. As it grows, it keeps accreting gas, and so the disk gets larger and larger as well. So you can see a bar forms in the center. The center has old stars, just like we see in real galaxies, and then the disk has new stars. So we'll watch that spin there for a second. And so it takes a couple minutes, but essentially, after the initial bunch of mergers with little things, this galaxy doesn't really have another major merger, which in astronomy, in technical terms, means it doesn't merge with another galaxy of similar size, because that might destroy the disk, and so then it would actually become an elliptical galaxy. And so it keeps swallowing little dwarf galaxies, which the Milky Way also has done, but generally it kind of is living in mostly in isolation from other big galaxies, and so it gets to grow a really big disk that it's accreting from the gas. And so that's kind of like what the Milky Way looks like. Okay, and so mergers of galaxies don't just happen in the very distant past. We actually observe them more nearby. So a lot of these well-known galaxy mergers are actually 50 to a couple hundred million light years away, which is pretty local universe. And so they're really pretty, and all this cool stuff you see here are when the galaxies merge, the stars kind of pass through each other because they're so far away from each other. And so when the gas collides together, it causes these huge bursts of star formation, and that's what you see here. And once all that is exhausted and all the stars get all mixed up, a lot of times you'll get a big elliptical galaxy because the two disks get destroyed by the gravitational interaction. So that's basically the end of my talk. And with this last slide, I just wanted to point out how cool it is that only a century ago, we were looking up at the sky and wondering about the nature of this galaxy, the Milky Way, that was all that we could see. And now we simulated their evolution over the last 10 billion years on a computer. So that's it. Thank you.
All right, thank you very much, Extragalactic Educator. We have time for some questions. Please shout out if I don't see you, because the lights here are really bright. I can see one in the front, though.
Yes, a spiral galaxy is clearly held in its place in shape, in fact, it spins. But what is it that makes an elliptical galaxy? Is it spinning? If so, what is its axis?
Okay, that's a really good question. So he's asking that a spiral galaxy is held in its shape by rotation and supported by rotation. So what gives an elliptical galaxy its shape? That's a really good question. So some elliptical galaxies are supported slightly by rotation, not as much as a disk, but a lot of them have what we call, they're supported by velocity dispersion. And so if you think about gas in a balloon, it keeps the balloon inflated is the pressure of the gas particles moving randomly around. So in elliptical galaxies, it's kind of a similar thing.
Okay, any other questions? Straight back. Oh, okay, right at the back, I see.
That's a really good question, and a lot of astronomers would love to know the answer to that. So the question was, when does the supermassive black hole form in the galaxy? Does it form first, or does the galaxy form first and then the black hole comes in? So that's not my area of expertise, but as far as I understand it, the supermassive black holes form during the epoch of galaxy formation. So it kind of forms concurrently in the very early stages of galaxy formation when galaxies are merging together.
And if you can answer that, you can get a PhD. Because we do see black holes that are like 1 billion solar masses right back only a few 100 million years after the Big Bang, and no one knows how they got there. So it's a very big open question. Yeah, I see one over here.
That's a really good question. So there are some special conditions that will cause, so the bar, just like the spiral arms, is a type of instability that forms in a fluid. And so we think of the interstellar medium, the gas and dust in the galaxy, as kind of a fluid. And so when you simulate it in a computer, and a lot of times if you include the gas and everything else, you will, and actually even just the stars, you will get a bar that forms. It's not exactly known the details of how they form, but people have worked out the physics. It's generally well known that it's just an instability in the disk, and so they form spontaneously, or sometimes gravitational interactions between galaxies can induce them.
Right back here.
Okay. The dark matter halo. So what exactly do you want to know about the dark matter? Okay. So you're asking the dark matter halo, what do we actually know versus the popular press? So we don't want to confuse dark matter and dark energy. Dark energy is still kind of an unsolved problem in astrophysics that people at UT are now working to hopefully solve very soon. The dark matter is basically pretty well established at this point. We know it's there because it interacts gravitationally with the part of the galaxy that we can see, the stars and the gas, and we also see its gravitational effects in clusters. The first evidence for the dark matter halos came when people measured the speed of stars and gas rotating in the outer parts of galaxies, and they were going way faster than they should have been going if only the stars and gas were actually there. So there must have been something else there that was causing them to go this fast. And so since we know actually a lot about gravity physics-wise, it was pretty easy kind of to work out that the dark matter has to be there. Now the details of the shape of the dark matter and its distribution, that's a little bit less well established, and people are working on those things. But yeah, we do know a lot about it, probably more than the